Hello and welcome. In this worked example, we've got a familiar water from a reservoir problem fed to a turbine of a hydroelectric system, gives us the mass flow rate 510 kilograms per second. The reservoir is 280 meters above the level of the turbine. This one is unique in the sense that it gives us the electrical output of the generator driven by the turbine, gives us the current and the potential difference, which remember is a voltage, okay? Right away, we can say, well, the power is current times voltage, right? So we just multiply these two numbers to get the power. But then we say, well, if this is an efficiency problem, and we know that efficiency is the useful power out, or what we like to call the POUT, over the total power in. And we can define this in terms of energy also. Well, the pin, the POUT over the pin, times 100%. That's how we remember efficiency. This one here is actually going to be the power out. The clue here is this word, output. Okay, so we're actually generating this much energy out, that much current, that much voltage. So our numerator is going to be the product of these two numbers. That's kind of nice. We say, well, how much power is going into this thing? Well, it's water from a reservoir, a certain height above, the level of the turbine. And so that sounds like some potential energy. How do you turn energy into power? Well, power is the rate that energy is converted. So it's always energy per time. They give us the mass flow rate. So potential energy, we can expand that and say, well, potential energy is mgh. And then where do we put this per time? Well, clearly underneath the mass, right? Because we got this mass, 510 kilograms of mass per 1 second of time. So this value here gets substituted in for m over t. G, we'll assume this is on planet Earth, where G is 9.81 meters per second squared, and the height is given over here, 280 meters. So let's kind of clean that all up. Efficiency, POUT over pin times 100%. The power out is going to be the product of the current times the voltage. So 205 amps times 5,800 volts, numerator's taken care of. The denominator is going to be the power in. We said that's going to be the mgh over t, and conveniently m over t is given. So that's just this number here, 510 kilograms. Put the units sort of back up here in the numerator, kilogram per second if we want to. G is 9.81. I'm going to use the units of newtons per kilogram. Meters per second squared and the newton per kilogram are the same thing. And then 280 meters. So the units here don't look friendly at all. What can we do? Let's see, kilograms are going to cancel. A newton meter is a joule. So you have like an amp volt per joule, and that should actually all cancel out to give us sort of the same units there. They say, well, remember that a volt is a energy per charge, and so it's joules per coulomb, and an amp we could say is a, let's see here, the intensity of current. So amps of current is charge per time, so coulombs per second. Well, we know the units are all going to cancel out anyway, so let's just see what the numerical value is, and then we'll consider the units in just a moment. Got a calculator check. Check my calculation. So that's divided by 510 divided by 9.1. So yeah, you get 8.848. So that's going to be 85% actually. So take care that just because this answer is 8.3, 83% is looking like, oh, that might be the best answer there, right? Because maybe you're thinking, oh, well, this answer is designed to capture those students that made some order of 10 error, and clearly the correct answer is 83, but it's actually 85%. All right, now let's take care of these units here. All right, so in the numerator, we had an amp, a volt, and a second, and the kilograms already canceled. So we have like amps, volts, and seconds. In the denominator, we have Newton meters, which is a joule. So maybe that's helpful. We just put the joule down here. All right, so the volt, 1 volt is energy per charge. Okay, so we have joules per coulomb. That's the unit of volts. Okay, so a volt is a joule per coulomb. I'm going to substitute that in right here. So we have this volt here. I'm just going to erase it. Is a joule per coulomb. So joules cancel. So we have an amp second per coulomb. Remember that an amp over here, an amp of intensity of current is a coulomb per second. All right, so an amp is a coulomb per second. So I'm going to plug that in. Amp, coulomb per second. So coulombs cancel, seconds cancel. We're dimensionless, just like we need to be. So remember, when we take this ratio here, we get like 0.848. So then the last step for efficiency is multiply it by 100%. So that moves the decimal point over 2. Add the percent sign, 85% is your best answer here. This is Dr. Schleith, still living the physics life. See you next time.